In this video, I will go over some of the predicted questions per topic for Paper 1 AQA A-Level Chemistry Exam 2025. Remember that this is not an exhaustive list of questions, but these are the most common questions that come, and I will focus on the most common topics that represent the majority of the marks of your exam. The first topic is reversible reactions and position of equilibrium and equilibrium constant. So in your exam, there will be a question about the Kp for gases, and this is the equation you're going to use using the partial pressure for the different gases for products over the reactants, each raised to the power of their number of moles. Remember that they're going to ask you to calculate the mole fraction of a certain gas, so that will be the number of moles of the gas over the total number of moles of gases in the mixture. And then you're going to calculate the partial pressure of a gas, which equals the mole fraction times the total pressure. Remember that temperature affects the value of Kp and pressure doesn't affect the Kp. The factors that affect the position of equilibrium, usually they ask about that. So temperature, depending on which direction of the reaction is exothermic. Pressure, of course, in case of gases only, and these are gaseous reactions that come in paper 1, and then the use of the catalyst, which doesn't affect the position of equilibrium. The type of question will come like these types. So it will be a different reaction from this one, but still going to be a reversible gaseous reaction. And they will ask you to calculate the mole fraction of each substance at equilibrium. They're going to ask to give an expression of the Kp for that reaction, calculate the value of Kp at a certain pressure, and state the unit of Kp. Also, they can ask about the effect of a changing temperature on the yield. Here for this reaction is on oxygen as one of the products, and the effect of Kp. Also, they can ask about the effect of the pressure on the Kp and on the yield. pH and buffers, one of the main questions that come in the exam, and it's always about calculating the pH or calculating the Ka of a weak acid. So these are all the equations that you're going to need to use in the exam. Of course, not all of them, but you're going to use some of these in your exam, but these are all the equations you need to know. So the pH is the minus log 10 for the hydrogen ion concentration. The ionic product of water equals the concentration of hydrogen ion times the concentration of the hydroxide. For pure water, the hydrogen ion concentration equals the hydroxide ion concentration. So the hydrogen ion concentration will equal the square root of the ionic product of water. The ionic product of water changes with the change of the temperature. So the pH of pure water will be different depending on the Kw. However, even though the pH changes, but pure water will always be neutral because the concentration of the hydrogen ion equals the concentration of the hydroxide ion, because this is one of the typical questions in the exam. Remember, for bases, to calculate the hydrogen ion concentration, we're going to use the equation for the ionic product of water, but here the concentration of the hydroxide ion will not equal the concentration of hydrogen ion, but rather will equal the concentration of the base used. And if we use a base that is from an element in group 2, for example, or a base that give you 2 hydroxide ions, it's going to be 2 times the concentration of the base. So hydrogen ion concentration will equal Kw over the concentration of the base. For weak acids, the dissociation constants of weak acids equals Ka, which is the concentration of the hydrogen ion times the concentration of the anion divided by the concentration of the acid. But because the concentration of the hydrogen ion equals the concentration of the anion, then we can calculate the hydrogen ion concentration as equal the square root for the Ka times the weak acid concentration. And finally, for buffers, the buffer will be a mix of an acid, weak acid, with its one of its salts, or it could be a weak acid with some base. So here the hydrogen ion concentration will equal the Ka A, again, the dissociation constant for the acid, times the concentration of the weak acid divided by the concentration of the anion, which is going to be the concentration of the salt if we add a salt, or it's going to be the concentration of a base if we add the base, because the base concentration will equal the concentration of the anion in this case. So the type of the questions that come will be calculate the pH of pure water at a certain degree, or calculate the pH of a solution formed from mixing a strong acid with a strong base. So here you need to work out which one will be in excess, what is the concentration of the acid or the base after the completion of the reaction, and then you're going to use this to calculate the hydrogen ion concentration. Calculate the pH of a solution formed from mixing a weak acid with a strong base. So this is for a buffer. We're going to use this particular equation, and then also calculate the pH of a certain solution of a weak acid, like propanoic acid solution. We're going to use this equation in this case, and then we have the appropriate use of the indicator. What indicator is most appropriate for a certain titration reaction between an acid and a base? That will depend on the use of a strong acid or a strong base, whether we are using weak acid or a weak base. Remember that if we use weak acid and weak base, the titration, you cannot use any indicator. Thermodynamics, one of the main topics in the exam. It's very common to get you an incomplete Born-Haber cycle and ask you to complete the cycle, where you need to write the samples and the state sample for each step in the Born-Haber cycle. They will ask you to calculate the enthalpy of lattice formation using the enthalpies from the table. Sometimes they give you the enthalpy of formation, lattice formation, and ask you to calculate a different one that is missing from the Born-Haber cycle. So you just need to work through the different enthalpies provided to get, using Hess's law, of course, to get to the missing one. Entropy change as well, one of the main topics, and I would think that this year there will be something about the entropy change. And if they ask about entropy change, they're going to ask about the Gibbs free energy and reaction feasibility. Remember that the Gibbs free energy is the delta G equals the delta H minus T delta S, which is the entropy change here. Sometimes, or a few years ago, they give you this a graph where they plotted the delta G against the temperature, and you get this straight line. And they ask the students to calculate the delta S here, or the entropy change, will equal minus the gradient of the line, or the gradient will equal minus delta S, and then delta H will be the y-intercept. So you can use the graph they give you to calculate delta H and the delta S. The enthalpy of a solution using the enthalpy of hydration and lattice enthalpy, also one of the common questions in the exam, again using the Hess's law. Some of the typical questions use the data in the table to calculate the enthalpy of solution of sodium chloride, for example. Calculate the temperature in degrees Celsius at which the reaction becomes feasible. Remember that for a reaction become feasible, the delta G will put it as 0. And in this case, the temperature will equal the delta H over the delta S. So you need to find the temperature. The temperature here will be in Kelvin, and you need to change it into degrees Celsius if they ask you to. Also remember that the entropy change usually calculated in joules, and we need to change that into kilojoules when we do the calculation. Complete the Born-Haber cycle, as I said as well, and maybe they will ask about the perfect ionic model. So remember what are the assumptions for the perfect ionic model and why there will be a change between the theoretical lattice enthalpy and the one that we get from the Born-Haber cycle or the experimental one. Electrochemical cells and electrode potential. So the most common questions are the calculate the EMF of a particular cell, give the conventional representation of the cell, give a half equation for the reaction that occurs at the negative electrode. So remember how to represent an electrochemical cell. You start with the electrode, and then you have the phase boundary, and then the oxidation reaction first, and then this is the salt bridge, and then the reduction reaction, and you end up with the electrode as well. Calculating the EMF, remember that the oxidation reaction will be for the one that has an electrode potential that is more a negative value or of a smaller value. And it usually takes place at the anode or the negative electrode, while the reduction will be for the species that has more positive or larger value, and it will take place at the cathode or the positive electrode. The EMF we calculated as the electrode potential for the reduced reaction minus the electrode potential. Sometimes as well, they give you an electrochemical series like this one with different values for the standard electrode potential. For me, I would think that this year they're not gonna give you this electrochemical series because it was a question last year in the exam. Probably this year it will be more focused reaction, a particular one, and they're gonna ask you which one's gonna be oxidation, which one's gonna be the reduction, and you have to work that out from the standard electrode potential. I remember that sometimes they ask you about why this reaction is feasible, or which one can oxidize the other one, or for a certain reaction, why it can, for example, here, why the zinc, for example, cannot reduce the vanadium 2 plus to vanadium, but it can reduce vanadium 3 plus to vanadium 2 plus. Remember how to answer this by using the standard electrode potential. So the standard electrode potential for the vanadium 3 plus to vanadium 2 plus is bigger than the standard electrode potential for zinc 2 plus to zinc, which means zinc can reduce the vanadium. But the standard electrode potential for vanadium 2 plus to vanadium is actually transition metals, complex ions, and their reactions, very common topics in the exam. You might get one or two extended questions about this particular topic. And for this topic, the type of questions depends on your understanding of what is meant by transition metals and why their complexes are colored. Remember, the subshell, the d subshell would split to give you two different orbitals of two different energies, and the electrons can actually be excited when they absorb light from the visible region into from the ground into an excited state. Remember the isomerism of the complex ion, the cis and trans, and the optical isomers. There were nothing about that in the exam last year, so it's a potential question in the exam this year where they ask you to draw the different isomers and state the type of the isomer. Remember the optical isomers, this is for the octahedral complexes when they have three bidentate ligands, where we have the non-superimposable mirror image, and then the cis and trans isomers, it's for octahedral complexes with four monodentate ligands of one type and two monodentate ligand of a different type. If the two different ones are opposite, this is a trans. If they are on the same side, then this is a cis. Also, the cis trans, we can find it in the square planar complexes with two pairs of ligands like the cisplatin and the trans one. So if the two similar ligands are on the same side, this is a cis. If the two similar ligands are opposite to each other, this is the trans. Remember the different factors that affect the color of the complex ion. Very common question in the exam. And these are the type of the transition metal, the oxidation state of the transition metal, the coordination number, and the ligand used. Remember the concept of the complementary color because they tend to ask you why this complex has this particular color. So you need to refer to the absorption of light, and then the color we see is the complementary color to the color that has been absorbed. The acidity of the 3 plus AQA ions of aluminium and iron. So remember that they have higher charge, and this higher charge will weaken the OH bond and will release more hydrogen ion into solution. So they tend to be more acidic than the 2 plus ions. Ligand substitution and precipitation reactions of ligand for the aqua ions. So remember that the type of question would be like give the formula of the precipitate that form in this particular reaction, give an equation for a reaction with like sodium carbonate, for example, state one observation a student would make from that particular reaction. So these are the four aqua ions and the reaction that you need to memorize before your exam. So please make sure that you know these very well because they definitely, some of these will be in the exam. Last year, it was about the iron 3 plus and iron 2 plus. So quite unlikely to be in the exam this year. So the focus would be more on the copper and aluminum, even though they might decide to ask about the iron. But I personally, I would think that there will be more focus on the copper and the aluminum. Please remember the amphoteric properties of the aluminum hydroxides. The mass spectrometry, one of the typical questions in paper one, the questions are quite typical. They like to ask about these two definitions, the relative atomic mass and relative molecular mass or formula mass. Please memorize these definitions because these are guaranteed mark. And then we have this big question with the calculation using the equation for the kinetic energy, which equals half mv squared, where m here is the mass of the ion in kilogram. And then the v squared is the speed they take when they move through the tube in the time of flight mass spectrometry. And the speed here is in meter over second. So remember, when they give you the distance in centimeter, you have to change it into meter. And remember, when you calculate the mass number at the end, and you need to multiply the mass of one particle or one ion by the Avogadro constant. Remember that the mass that you get from here is in kilogram. You have to change it into gram and then multiply it by the Avogadro constant. Also remember and focus very well on the type of the ionization, whether it's electron impact or electrospray. So if it's electron impact, then that means the mass number you get at the end when you multiply the mass by the Avogadro constant will equal the mass number of the ion. But if they use electrospray, then the value that you get at the end will be the mass number plus 1 because we added a proton to the ion. One of the typical questions as well is to ask you to give the equation, including the state sample for the formation of strontium plus, for example, ions from strontium ions by electron impact. Remember how to write these equations and practice these type of questions as well. Titration, very common question, definitely going to be in the exam. It's usually back titration, sometimes two different questions. One of them like an acid base with a back titration. The other one is like a redox where they use the transition metal and use the transition metal and the oxidation redox type of reaction for transition metal. Remember to use the balanced equation, and remember for your calculation, start from the bottom and work your way up. Like this question, for example, from last year exam. So there are several steps where they first reduce the vanadium VO3 minus to convert it to VO2 ions. All of them are converted VO2 ions, and then they are reduced to vanadium 2 plus, and then with excess zinc, and then back again, they have been oxidized from vanadium 2 plus to vanadium O VO2 plus using potassium permanganate. So to work through these questions, you have to start from the bottom, as I said. So first of all, you need to use the amount of the titrant here, which is the potassium permanganate, and to calculate the amount or the number of moles of vanadium 2 plus. And then you're gonna work here upwards to convert this vanadium 2 plus to vanadium O2 plus, which is basically going to equal the same number of moles of the original substance. And then they usually ask, for example, here to calculate the percentage purity of your compound. So when you do your calculation, find the number of moles, multiply the moles by the MR to find the mass. Then you're going to find the mass that you found divided by the total mass of your sample times 100 will give you the purity. There are three elements and their oxides. So these are not massive questions. Usually the inorganic part about the group 2, group very 3, and the group 7. Most of the time they come as one question that have several questions about all of these topics together. So the most important thing about period 3 is because it hasn't been largely in the exam lately, so it might feature actually in the exam, is to remember the difference or the trend in the melting points for these. So remember, from sodium to aluminum, high melting point due to the metallic bonding. You have to explain the increase in the strength of the metallic bonding by increasing the positive charge and the number of delocalized electrons. For silicon, it has a very high melting point because it's a giant covalent structure. For phosphorus, sulfur, and chlorine, they all have low melting point because they have simple molecular structure. So they have weak van der Waals forces of attraction. Remember that the melting points will peak at the silicon and then will drop sharply after they might ask you to explain the trend. And don't forget the acidity and basicity of the period 3 elements oxide. So the metal oxides are basic, aluminum oxide is amphoteric, and the silicon oxide is weakly acidic, but it's insoluble because you know that silicon oxide is giant covalent structure. And then phosphorus and sulfur are acidic, and when they dissolve in water, they will give you acid, which is phosphoric acid or sulfurous acid for sulfur dioxide. For the sodium and magnesium, they will give you the hydroxides when they dissolve in water. So it's very common in the question to ask you to write an equation for a reaction between an oxide and a base or shapes of molecules will always be in the exam embedded within other questions, and they're going to ask you to draw the shape of a certain molecule. You need to memorize all of these shapes. I'm not going to go over them one by one. You can just take a screenshot for this slide, and you can revise these ones based on the number of the bonds and the number of lone pairs. Don't forget how to predict the shape of the molecule, or how to determine the shape of the molecule using these rules, where we need to find the number of bonds and the number of lone pair of electrons around the central atom. So you need to decide which atom is the central atom, then how many electrons are there in the outer shell, how many outer shell electrons are there, that will depend on the group number, and then add one extra electron there for each atom, for each bond, and then divide this total by 2 to find the total number of electron pairs. Take away the number of bonds, then you're going to get the number of lone pairs. So once you find this, you can use the list of the different shapes here, depending on the number of bonds and the number of lone pairs, to find the shape and the bond angle. So the typical questions: draw the shape of a particular molecule, name that shape, what is the bond angle, and explain the bond angle. When you explain the bond angle, you have to refer to the repulsion between the lone pair is greater than the repulsion between the lone pair and bonding pair, which is greater than the repulsion between bonding pair and bonding pairs. For the group 7, so the reaction of group 7, the chlorine with water, was one of the topics in the exam last year. So for me, I would think that it's quite unlikely to be in the exam again this year. But what wasn't in the exam was the trend in the reducing power of halides ions. So make sure that you go over this topic. Remember that chloride and fluoride were both of them, when they react with sulfuric acid, will act as a base. Just to give you hydrogen chloride, the sodium chloride will give you hydrogen chloride and sodium hydrogen sulfate. It's not a redox reaction. Bromide will reduce the sulfur in the sulfate ion to give sulfur dioxide only. It's not going to reduce it further to give hydrogen sulfide. In case of iodide, because it has higher reducing power, it will reduce the sulfate ion to give sulfur dioxide, and then will reduce it further to give hydrogen sulfide. You don't need to memorize the balanced equation, because you can work it out yourself by working out the half ionic equation, or working out the reduction and oxidation, the half equation for the reduction and oxidation, and then combine these two to give the full equation. Don't forget the test for the anions, which are the test for halides. This hasn't been in the exam last year, so probably will be this year. So chloride, bromide, and iodide using the dilute nitric acid and then silver nitrate solution. When we get a white precipitate with chloride, cream with bromide, and yellow precipitate with iodide. And then further test for the precipitate using the ammonia. Dilute ammonia, silver chloride will dissolve. Concentrated ammonia, silver bromide will dissolve, and of course, silver chloride as well. Silver iodide will not dissolve in either of these. The test for sulfate, we need to add a dilute acid followed by barium chloride solution. A white precipitate of barium sulfate will form. And then the test for the carbonate will be with addition of any dilute acid that will give you carbon dioxide. And the carbon dioxide can be tested further by lime water. Remember the flame test for the group 2 elements, or ions. So we only need to know these three: calcium, strontium, and barium. Calcium will give you brick red flame, strontium will give you the red flame, and barium will give you the pale green. The test was sodium hydroxide. So magnesium is the most insoluble, so it will give you a white precipitate. Barium is the most soluble for the hydroxide, and there will be no visible change. Test for the ammonium ion, you need to add sodium hydroxide